like to talk about the nonlinear functions we often see in neural networks and other neural types of related algorithms. And what we're typically looking at is we're going to have a vector matrix multiplication and then some nonlinear function afterwards. And this combination of inputs through outputs is what we define as a layer. And layer in typically any sort of neural network structure. And what's interesting is typically this f is going to typically be a function with no dynamics and no cross terms. So typically what I would find is if I had a vector v vector v in here, that goes to a vector y here, and each of the terms sub k directly go to those k. So you get this kind of term here. Now there's a couple, there are exceptions to this. Dynamics you might see, for example, if I'm doing a Hopfield network is a very classic case of that. What I may also imagine is if I might imagine some cross terms if I'm doing a winner-take-all network. There I will definitely see some other dynamics as well as cross terms. But most cases you're going to see things that don't have those components to it. So now we're talking about, various terms, and typically we're going to want analytic functions because that's going to make a huge difference when it comes to training. Analytic means all derivatives exist everywhere. That'll be huge. Now, a good example of one that doesn't is the classical McCulloch-Pitts that goes back to 1943. And this, again, just looks like a unit step function. There could be a threshold, it could get moved. This became the key behind building perceptrons. This sort of nonlinear function that's discontinuous. The discontinuity also caused a huge issue that meant that most of these kind of learning algorithms didn't show up until people learned to make this more continuous. The continuous function you talk about are sigmoids, which is usually meaning some form of a hyperbolic tangent. So this could be either going from -1 to 1 in this case, so hyperbolic tangent. And you also get, for example, depending on what the gain factor is here, that gives me it either steeper or shallower. Now this hyperbolic tangent function definitely has its roots in circuits, which is where a lot of times you'll see this come out of. And it comes out of that sort of neuromorphic community realizing this was important for differential pairs. And so this was something that was very, very important and used in many, many places. You could see this being done -1 to 1. You could see it being done from 0 to 1, which is a little bit more of the earlier functional form, where you might just say tangent plus 1 over 2. Again, you can see that I can get different levels gained depending on how I change things there. And this is one that, for example, Hopfield, certainly from his classic paper in 1982, started to look at this question. And it's usually in these discussions where you start talking about this has an approximation of average neuron firing rate. And Hopfield made this argument, and others would go, well, maybe I've got something that looks like, I get close to a threshold, I start to see something happen, I get a linear dependence, and then eventually the neuron gets tired and kind of slows down. And so this gives you kind of an interesting weighting, but it gives me a function that's analytic. And that's useful if I'm building nonlinear dynamics that I need an analytic function. It's such as Hopfield will use. It's very important to take that concept and go, wait, I could build backpropagation algorithms now out of this because I can do derivatives on the structure. This is huge. And so you'll see this used a lot of times all the way through this. One of the other functions you'll find is if you were to take like this blue curve and integrate it with the input variable, which is basically, again, an analytic function, but it looks like it's basically sort of a rectifying function. And so it looks like it's pretty much 0. It looks like it pretty much becomes almost proportional to the input, and then there's sort of a continuous term in between. And this turns out to be very, very valuable, and a lot of times people like to use this for a whole range of learning algorithms. There's advantages, disadvantages to these approaches, but it still gives you a nice nonlinear function that is analytic if you use it properly. And so all of these things give me some really interesting learning algorithms and properties I can work with over a whole range of different types of applications.